So this is the first talk in the afternoon. Hope we can keep you sleepy and wake you up sometime in the talk. So this is Zhen Xiao, and this is my colleague Nazi. We are both working in the big data platform team at Netflix. And today, we'd like to share our experience about Presto. What will I talk about? I will start with a brief introduction about our Netflix big data platform. And then I will talk about what Presto is and how we make Presto work. Nazi will cover the details about our deployment and integration. Then we will go through some of the technical details to show you how Presto works internally and our contributions. Finally, we will share our roadmap about Presto. So where does our data come from? At Netflix, we have two data pipelines. One is the event data pipeline. Another one is the dimension data pipeline. For event data, you can think of whenever you do a movie search on the Netflix website, or you click for movie details. That we call the event data. We have over 500 billion events per day, and all these data are coming through our data collecting tool. We built a tool called Zero, and now we are transitioning to make Kafka to be integrated into our ecosystem. After going through this data collecting tool, all this event data will coming through our internal tool called Ursula, which will separate the data based on the event types, and then merge them and store them on S3. The SLA for this event data pipeline is 15 minutes, which is to say, whenever an event happens, we guarantee that the event data will reside on S3 within 15 minutes. Another data pipeline is a dimension data pipeline. What is dimension data? You can think of all the Netflix user subscription data as the dimension data. As you may know, Netflix is using Cassandra to store all of our dimension data. And we built an open source tool called Agathis to incrementally backload the data from Cassandra and store them on S3. We do this daily. So by the end of the day, both of our data pipelines will store the data on S3. We have over 15 petabytes of data. What shall we do with this data? Let's take a look at our big data platform. So this picture will show you all our existing systems in the big data platform. From bottom up, we are storing everything on S3. That is our source of truth. We are separating storage from computation. That is the key underpinning of our architecture. And we built an open source tool called Sample to work around the eventual consistency problem. Amazon also is incorporating the similar functions into their EMR file system. On top of the storage layer, we have the compute layer, where we have Hadoop clusters to run MapReduce jobs, and we have Presto clusters to run the interactive jobs. We are also evaluating Spark and Yarn to see whether it can complement our existing system. On top of the compute layer, we have the client systems, where we are using Pig for ETL processing, and we are using Hive for reporting and other analysis. We are using Presto for interactive queries. And we are also using Scoop and Druid for other tasks. On top of the client systems, we build services, where we built and open source the service project called Genie. Genie is a federated execution service for all our data scientists. So our users can submit a query via REST API without need to worry about all the configuration stuff. And also, we provide this Metacat, which is a data catalog service for all our data sources. including the Hive tables, relational databases, and even S3 files. On top of this service layer, we have the tools layer, where we provide this big data API and big data portals. The big data portal is a very user-friendly portal for our users to submit a query and choose whichever engine they would like to run. Also, we built an open source a tool called Inviso, which is the performance visualization tool for our users to debug and tune their MapReduce drops. So in general, we have two kinds of use cases. One is the batch drops, where we are using Pig for ETL processing, and we are using Hive for reporting and other analysis. There is another important type of drops, that is the interactive drops. What shall we do with them? Well, there are a number of tools available in the market, and we evaluated some of them. They are either not fast enough, or they doesn't work well with S3, or they need some special ETL processing to load the data into the engine, or they do not use the memory efficiently. So finally, we choose Presto. What is Presto? Presto is an open source distributed SQL engine for running interactive queries against large data sets. Presto is open sourced by Facebook in October 2013, and we put it into production in March 2014. The Facebook Presto team did an awesome job for creating this tool, maintaining the tool, and also reviewing our code. So we are really happy with using Presto. And why we love Presto? The number one reason is Presto is fast. It's very fast. It's super fast. It's extremely fast. And you can see the performance comparison based on our own benchmark, which shows a comparison between Presto and Hive. You can see that Presto is always 10 times faster than Hive. And in some cases, it is even faster. Why Presto is fast? Since Presto is doing in-memory streaming processing, it never hit the disk. And also, Presto does not use the MapReduce framework. It is built from ground up. And it generates bytecode to process the database operations. Another good thing about Presto is scalable. Facebook has a number of Presto clusters, and the largest of them consists of hundreds of machines. Our deployment also has hundreds of machines, which Nazi will talk about in detail. Also, Presto provides ANSI SQL, so we do not need to teach our user to learn a new language. Everyone knows SQL. Presto is open source, so we can maintain our code, patch it, and finally contribute back to the community. One good thing about Presto is it works well with S3. As I said, all of our data resides on S3, and this Presto working with S3 make it easily to be fit into our big data platform. Another thing is Presto is Hadoop friendly. So it is running good with the HDFS and the Hive metastore out of box. And as you may know, Netflix is a heavy Hadoop user. So this Hadoop friendly make it easy to be integrated into our Netflix ecosystem. So now, my colleague Nazi will continue talking about our deployment and integration.
Thanks, Nizar. Okay, good afternoon, everyone. So I would like to first start with an overview of our production deployment. So we currently have Presto version 0.100 running in our production. And it's currently running on Java 8. And we have a single coordinator in our production environment and around 220 worker machines, all of which are running on the R3 for Excel EC2 instance type. And this instance type is optimized for memory-intensive applications such as Presto. And when you look at the clients that access our deployment, we have a wide variety of them, from Presto's own interactive command line interface to third-party libraries for programming languages like Python and R, and also a bunch of other tools, including business intelligence tools that use ODBC and JDBC interfaces. And here are some interesting facts about our deployment. So we currently have around 300 plus internal Netflix users that use Presto. And these users run roughly around 2,500 queries a day on average in our system. And all these queries run against our data warehouse on Amazon's S3 storage system, which has a total size of more than 15 plus petabytes. And you look at the query runtime distributions of our production queries, you will notice that half of them run less than 4 seconds. And in fact, 85% of these queries run less than a minute. It's not bad. And we have also some longer running queries that take several minutes, which depends on the amount of data that they process and the computation they perform on these data sets. And when you look at the data size processed by all these queries, the data size distribution, you see like the half of the queries process less than 100 megs. And of course, there are larger queries that process from several gigabytes to several terabytes. OK, after deployment, let's take a look at how we integrated Presto with Netflix tools and services. But before really going into all these details, I'd like to first visualize our deployment. And like Jinshao mentioned, all of our data sets reside on Amazon's S3 storage system. And all our clusters are running on Amazon EMR. EMR standing for Elastic MapReduce Service of Amazon. And the big rectangle that you see in this slide is our production deployment. And there is single coordinator marked as red here, and a bunch of worker machines. And on all these machines, we have 2 processes running. One is the Presto process itself, that's marked as green, and also a sidecar process, marked as blue, which is kind of the glue between the Presto deployment and our services. And as you see here, the coordinator talks to some external systems, the first one being the HCatalog server. The coordinator uses the HCatalog server to pull down the metadata during query planning. And the metadata is, in fact, stored in an Amazon Relational Database Service instance, which you can think of as a single MySQL instance. And the coordinator also talks to our internal data pipeline called Suro to publish some query-related events, which I'll describe in the next slide. And finally, all these machines in our Presto cluster publish periodically various performance metrics to our telemetry system called Atlas, which is also an open source Netflix tool. Now, we have been through 3 major steps to integrate Presto with the Netflix systems. And number 1 is our efforts with the data lineage. And you can think data lineage as being able to trace back the sources of some data set and understand this evolution over time. It sounds simple conceptually, but when you have a large warehouse, data warehouse, that you have lots of users that are running a lot of queries and you have a lot of tables, it's hard to track all these dependencies. It can get messy quite easily. And to track data lineage, we extended the coordinator logic to publish query completion events. When a query gets completed, the coordinator publishes a single event to our data pipeline, Suro. And you can think this event as a JSON document, which contains the user that submitted that query, the query SQL string, and a bunch of statistics. And this event gets written to a Hive table, which is backed by S3. And we have an internal data dependency analyzer tool called Charlotte. And Charlotte periodically scans this Hive table and then understands and extracts the dependencies of queries onto our Hive tables. So when we go to the Charlotte web UI, we can easily see which queries depend on which tables. And we can understand what may happen if we change a table, what impact it may have in the depending queries. And also, we can understand which tables aren't used by any query at all. Number 2 is monitoring support, so which is, in fact, a very important concern for productionizing an open source system like Presto. Presto, out of the box, comes with various performance metrics that you can hook into. It exposes a lot of metrics through the Java management extensions, the JMX interface. We initially actually extended this set of metrics with various metrics that we care about, like the metrics at the file system, the S3 file system level, where Presto talks to S3. And then we also deployed a sidecar JVM, a Java virtual machine process, on all the machines so that we can pull down these performance metrics periodically and then push these metrics to our telemetry system called Atlas. And then when we hit a problem in production, we just go to Atlas Web UI and then slice and dice those metrics, visualize them to understand the root cause of the problem. And the last item is business intelligence tools integration, or BI tools integration in short. So at Netflix, we have various teams that use popular BI tools such as Tableau and MicroStrategy. Previously, they were using Hive to access our data warehouse. But once they experience the performance of Presto, they want to switch over to Presto immediately. And we have spent some time integrating these tools with Presto. And recently, and we have been through actually several efforts for MicroStrategy and Tableau. And recently, MicroStrategy announced with their version 10 that they will support JDBC connectors. So we have been testing that for some time, and we will continue testing MicroStrategy's JDBC support for some time with Presto's open source JDBC driver. And if everything goes well, we'd like to roll it out internally. So this was not bad, but when we tried integrating Presto with Tableau, we have spent more time with it. It was a little bit more complicated. First, we looked at Presto's ODBC driver, which is written in the D programming language and which is still kind of experimental. We spent some time with it. We fixed some bugs. We made some contributions. In fact, we made the very first public release to make our users' job easy to install these drivers on their client boxes. But there was still a big problem with it. And the problem is, if you have a query that returns large result sets, the ODBC driver was buffering the whole result set in memory before returning to the application, in this case, Tableau. So it was easily running out of memory. And we were looking for alternative solutions to this problem. And recently, Tableau announced with their beta 9 version that they will support a web connector API, which is for hooking into any web resource, an arbitrary web resource. And for that, you need to write several JavaScript functions, and Tableau will hook into that functions and fetch the data and the schema information. And we put together something for Presto. We put together a Presto web connector for Tableau. And we have been testing it right now, and we will continue testing it in the near future. And the thing is, the initial results are pretty promising. So our users reported that they were able to pull down several millions of records without hitting any memory issues. So if everything goes well, we would like to, again, use it in production more heavily and hopefully open it up for the wider audience. Having said that, I would like to, again, leave the stage to Jin Shah to walk you through some of our contributions.
Thank you, Nazi. So now I will go through some of the technical details and talking about our contributions. So here is a summary slide which shows what we did to Presto. In query optimizer area, we are doing 2 query optimizations. One is to rewrite a single distinct query into group by query. Another thing is we rewrite a join query with similar subqueries into a simple aggregation query. Both of these will improve the query performance. And in the type system, we are adding a number of new functions to the complex types to bridge the gap between Hive and Presto. Also, we make the array type and row type comparable so that they can be used in a group by query. One big thing we did is for the Presto S3 file system. Since all of our data is stored in our S3, and we contributed to the initial version of the Presto S3 file system. In addition, we did a number of things, including multi-part upload, instance credentials support, also the AWS role support, and we did exponential backoff, retries, and a number of bug fixing to make the S3 file system reliable. Now, they are in production quality. One other thing we did is for the Parquet file format support in Presto. Parquet is a columnar file format, and it is supported in Presto. We did Schema Evolution for the Parquet support in Presto. And also recently, we make Presto upgraded to the latest Parquet version, which is 1.6. We also fixed a number of bugs to make these working. Actually, we are using Parquet in most of our data warehouse. And most of our data is in Parquet file format. Now, Z will talk about this in detail. Now, this graph will show you internally how Presto works, and I will go through it. Presto supports a number of clients, including ODBC, JDBC, the Presto command line, etc. And all of these clients will submit a SQL query to the Presto's coordinator. Whenever the coordinator gets a SQL, the parser will pass it into an abstract syntax tree by referencing the type system and the functions catalog. The parser will also do some type checking and validation stuff. And then the parser will send the abstract syntax tree to the optimizer, where the optimizer will build a logical plan and then applying a number of rules to optimize the plan. And finally, the optimizer will send this optimized logical plan to the distributed planner. The distributed planner will distribute the plan and chunk it up into plan fragments and send it to the scheduler. Scheduler will assign tasks to all the workers. Now let's take a look at the worker side. Whenever a worker gets some tasks from the scheduler, it will start reading files from S3 and then do some computation. And finally, the clients will pull results from one output worker. Now, let's take a closer look at the optimizer and see our contributions. The first contribution we did is to rewrite a single distinct query into a group by query. Why we are doing this? The general idea is to push partial aggregation as early as possible so that we can distribute the distinct computation and also reduce the network load between the partial aggregation and the final stage. Let's take a look at an example to the left. You can see a simple query, select count distinct C from table T. And the original plan is something like, also in the middle. You can see we first do a table scan, then we compute the distinct, then we compute the count, and finally we get the result. This can be optimized. We can rewrite that in an optimized way, where we do a table scan first, then we do a partial group by based on the key, based on the distinct column, and then we do a final aggregation. Then we are done. So in this way, the distinct computation is distributed, and also the network load between the partial aggregation and the final stage is reduced. This will improve the query performance. Another thing we did is to rewrite joins. Let's take a look at this example to the left. This is a little bit complex, but it's a simple join with two relations, where these relations are scanning the same table, grouped by the same key, which is the join key, and the only difference between these two relations is their aggregation functions. So the original plan is something to the right. You can see the table is scanning twice, and then compute the group by and all the aggregations, and then you do a join. This is expensive. We can rewrite that into a simple aggregation query, which is something like this. You do a table scan, then you do the group by and all the aggregations, then we are done. So in this improvement, based on our benchmark, we can see the query performance improve at least 2x faster than before. And now, let Z continue with all of our other contributions.
Okay. Now let's take a look at our contributions to the complex type support in Presto. So Presto currently supports 3 different complex types: arrays, maps, and rows. Rows are similar to Hive structs. The main goal of these contributions is to bridge the gap between Hive's complex type functionality and Presto's complex type functionality, so that when our users want to move over to Presto, they don't need to change much of their SQL scripts for complex type processing much. Initially, what we did is to contribute various functions like map keys, map values, to get the keys and values of a map, and array join, like to create a string out of an array, etc., which already exist in Hive. And then we also contributed comparability support, which enables the user to specify these complex types in group by statements, or for example, in partition by statements in window functions. And finally, we have contributed a number of fixes, especially for handling edge cases like null elements or negative indices. Okay, after step 5, now the workers receive the tasks to run. Now they need to read the data from S3. And for that, there's an S3 file system implementation in Presto. And it provides a very nice abstraction on top of Amazon's S3 key value store. And you will see methods like, when you look at the interface of this file system, you'll see methods like read, write, open, close that you will see from other file systems. And what happens under the hood is these method calls are converted to S3 API calls, like get object or list objects or get object metadata, which eventually get boiled down to various HTTP calls to AWS Web Services backend. So like Jinxiao mentioned, we first helped the Facebook team to release the very initial implementation, and then we made a number of contributions. And in fact, I will mention four of our major contributions to the S3 file system implementation. Number one is multi-part upload support. Previously, Presto was using S3 put object API call to write data to S3. And with put object, only a single thread is doing the writes. And there's a cap on the amount of data that you can write to S3 with this single call. So this was kind of inefficient. So what we did is to use multi-part upload capabilities of the S3 API. And now the writes are being done with multiple threads, utilizing the hardware, the cores of the machine and the network better. And also, we don't have any limit on the amount of data that we can write with a single call. So we got rid of that limitation too. Our second contribution here is instance credential support. Previously, Presto was only supporting static credentials. That's, you need to store the secret keys for your account on the worker machine's disks, which is not secure, of course. So with the instance credential support, we got rid of those secret keys from the workers' disks. And now the workers will go ahead and ask the instance metadata service that's running on all the EC2 instances. So they will just fetch those credentials and then access S3. Number 3 is assume role support. Assume role is, you can think it as a special function call that will give you some temporary credentials, a temporary key to some sensitive data, let's say. And with this, now the workers can assume a role temporarily to access sensitive data. And you can specify this role, temporary role, this special role, with some session parameters in Presto. And the final item is we made some contributions to the existing exponential backoff retry logic in Presto. And in fact, we have made it much more configurable so that we can fine-tune it and then make it behaving much more predictable in production, and also fix the number of bugs to make it much more reliable at our scale. Now, at this point, the workers have the data from S3, but it's raw byte stream. It's a stream of bytes. And to decode those bytes and understand what's in those bytes, they need to know which format, which file format has been used to write those data on S3. And we are using the Parquet file format. And in fact, 70% of our data warehouse is in Parquet format right now. So what happens next is the workers feed those byte streams into what's called the Parquet Hive record cursor in Presto, or Parquet cursor in short. And then the Parquet cursor does its magic to understand what's in it and then push the data further on the next stage of the workers. And we have made a bunch of contributions to Presto's Parquet support. But before going into the details, I'd like to take a minute to show how a Parquet file looks like. So Parquet is a columnar file format, as opposed to being row-oriented. And it was started as an open source project several years ago by Twitter and Cloudera. And some of the ideas for especially storing nested structures was inspired by Google's Dremel paper. And when you zoom into a Parquet file, what you will see is there's a number of row groups in it. And you can think of a row group as a set of rows. When you zoom in further, you will see multiple column chunks in a single row group. And in fact, a column chunk for every column in your data set. And these column chunks can be encoded and compressed by Parquet independently, so that depending on the data type, Parquet can choose the best compression and encoding method to use, so you get better compression. Zoom in further, you see multiple pages in a column chunk. And a page can be defined as the smallest unit of data that Parquet can operate on. Now you will see multiple row groups in a Parquet file, and towards the end, there's a footer section. And in that section, first you will see some schema information which will tell you the name and the types of these columns. And you have a bunch of other information. Again, there's a hierarchical metadata information section here. And in that, there is first the row group metadata, including some encoding and other information. And if you zoom in, you will see column metadata information that has some useful statistics that can be used in optimizing the table scans. So our main contribution to Presto's Parquet support is to improve schema evolution, improve the schema evolution support of Presto. So I would like to describe this with a very simple example. So assume that you have a table with a column named zip code, and you have written some data with it. And later on, you did an alter table, and then changed the column name from zip code to postal code. Now, if you run a query with Presto, like select postal code, Presto will go ask the Parquet library, give me the column with name postal code. And this will fail with the old data set, because there's no such column. It was zip code there. So what we did is, instead of Presto asking for columns with name, we let Presto ask columns with indices. So that will ask, like, give me the column at index 2. And this will make your query go through. And this behavior is currently configurable, by default being index-based access. So this gives you quite some flexibility when you change the column names and the column ordering. And the second major contribution for Parquet from our team is upgrading Parquet from version 1.3 to 1.6 in Presto. And for that, we have fixed a number of bugs in the Parquet record cursor and contributed it back to the community. And finally, we have also contributed a number of minor bug fixes so that Presto can handle structs that are Parquet encoded. Now, after talking about all these boring technical details, I would like to share some of our interesting roadmap with you. And we have 3 major items in our roadmap. The number one is being about Parquet optimizations. And we have a number of optimizations that we want to do in the near future, hopefully. And the first one is vectorized reader implementation. And it is still in progress. We are still working on it. And the idea is, instead of getting one row at a time from Parquet library, you'll now be able to get a batch of rows at a time, which is hopefully more cache and compiler friendly when you think of the JVM optimizing for loops much better than individual instructions. Number 2 is predicate pushdown. So the idea of this optimization is to, when you write a SQL query with a predicate in your where clause, we would like to push this predicate all the way down to the Parquet file format level, so that we can use the statistics that I mentioned in the previous slide in the column chunk metadata to skip some of these row groups while scanning a Parquet file. Number 3, lazy loads. And I think it's easy to describe this with a very simple example. So assume you have 100 rows, 100 columns, and you do column projection to get the first 10 columns out of it. And then say you have a predicate that only references column number 1. Okay? If the predicate does not hold for any of the rows in the first column, you don't need to load the remaining 9 columns. So this will save you some I/O. And very similar to this, you can also apply a similar optimization like lazy decompression and decoding, or materialization in short. Again, you have 100 columns. You want to project on 10, and you have a predicate addresses the first one. If it doesn't hold, you don't need to decompress or decode or even touch any of the remaining 9 columns. So you can simply move on. And all these optimizations applied to the file format level will hopefully yield significant benefits. And in fact, Presto team has written a recent blog post about it, where they apply most or all of these optimizations to the ORC file format. And they have demonstrated speedups from 2x to 6x in their benchmarks. And even under some cases with predicate pushdown, they report like 30x speedups. So that's pretty impressive. So the second big item in our roadmap is better resource management. So Presto currently supports very basic resource management. And in particular, we are interested in implementing a graceful sharing mechanism. So when we say graceful sharing, we want to actually decommission worker nodes during runtime without failing any queries that is running on that particular worker machine. So this is particularly useful when you think about cloud deployments. So if you have a period of time in your production environment where the workload intensity gets lower, you may want to free up some resources. And this feature will be useful. And the Facebook team also has some resource management related items in their agenda, and they already started doing some pretty interesting work, especially regarding cluster memory management. The final item is better business intelligence tool integration. Like I mentioned, we are still testing MicroStrategy's JDBC support, and we have written a Presto web connector for Tableau, which we are still testing again. So if everything goes well, hopefully we will make it rock solid and production ready and share with the community as an open source tool. So we have been using Presto in production for over a year. And we are very happy about its performance. It has worked very well for our interactive use cases so far. And all these contributions that we talked about today with my colleague Jin Xiao, most of them are integrated into Presto. And they're all open source. And we think and we hope that all these contributions are not only useful for Netflix users, but also useful for other big data users who have similar interactive use cases. So it's all open source, as I said. So please go ahead, check the GitHub page of Presto and check it out, give it a try. And please keep following our work. So we'd like to thank you all again for attending this session. And we'll be happy to take any questions you have. Thank you. So if you have any questions, please use the microphones on the sides.
Hi.
Hey.
Do you guys use custom functions, UDFs heavily in Hive, and did you have to work on porting them to Presto, or did you get them to work directly in Presto?
So currently, Presto does not support UDFs. So what you can do is try rewriting your UDF instead of by using SQL primitives. That's one option. Another option is to implement that UDF and package it with Presto and deploy it to your cluster.
Sorry. So if you package it with Presto, then how do you invoke this custom function in Presto query?
Okay, can you repeat that again?
So you're saying package the UDF with Presto, right? Then how do you invoke it in the Presto SQL query?
So if you package that function in Presto, it will be available in the function catalog. So you can refer to that function in your SQL queries. And the parser will not complain about it, because it will see that in the catalog.
Okay, thank you for the nice presentation. So I noticed in first beginning few slides that some of your queries are working on a very large data set, and they are coming back in like 4 seconds to like anywhere, if the data is more than in 10 minutes. I'm trying to figure out what are the major optimizations, or what are the bigger bang for the bucks that you have? Like, do you do partitioning, value-based partitioning, hash-based partitioning? What are the things that makes your queries very fast?
So there is a number of contributing factors to that. Like you said, partitioning is one part of it regarding the physical layout of the data. We do partitioning at the Hive part of it. But there is a number of other things that contribute to the good performance. One being, for example, the Parquet file format, so that you only read the columns you want. Okay? And the other part is mostly thanks to the architecture of Presto. So it reads the data off of the disk once. And it streams that data through the memory and through the network. So everything is in memory. So you don't touch the disk again. So it's not only about partitioning, but at multiple layers of this stack, there's a lot of optimization that's going on to really speed up this processing.
Okay. Actually, one follow-up question I had was, so as you mentioned that your data is streaming from bottom to up, like scan to join to aggregation kind of. What happens if one of the node which was processing the data fails, like in the middle of the query? How do you recover from that?
Yeah, that's a good question, and that's some of the features that's still missing in Presto. So Presto currently doesn't handle worker failures. So if your worker fails in the middle of a query, you lose that query and other queries that are running on the same worker. So that's still missing. So if you want, please go ahead and contribute that feature. We'll be very interested.
I've been thinking about how to do that. So if I come up with something,
Yeah,
definitely.
yeah, please ping us.
We do have retries and exponential backup at I3 level. We don't have the fault tolerance at the task level.
Okay, guys,
So
we
you
have
can
run out of
contribute
time.
that.
So if you have any questions, we are here. So thanks again. And by the way, I would like to make a small announcement. There is another session by Teradata people at 2:35 p.m. where they will share their roadmap regarding Presto. So that will probably be very interesting. I'll say go check it out.